Hello and welcome to lecture number 7 in the course Advanced Robotics Applications. In the last class, I had discussed about kinematics and we had solved the problem of forward kinematics and inverse kinematics of a 2 degree of freedom manipulator, which is a planar manipulator, which is probably the simplest manipulator that you will get. Now today I will discuss a little bit further. I will talk about the inverse kinematics of the 6 degree of freedom Puma robot. In the last class, I had also explained about the DH parameter table of the Puma robot. So the Puma is an industrial robot which has 6 degrees of freedom, 6 revolute joints. And there is a systematic way in which we have to solve the inverse kinematics. Otherwise, we are unable to solve the inverse kinematics of large degree of freedom systems. After that, we'll move on to sensors and actuators. Now, before I start solving the Puma inverse kinematics problem, I will explain very quickly about how the general inverse kinematics problem is solved. Okay, what is the formulation of the general inverse kinematic solution? That is, you are given desired position and orientation of the end effector, and you're asked to find the joint angles. So the procedure of solving it is to first find the transformation matrix that relates the end effector position and orientation with respect to the base frame, and then equate that matrix to the position and orientation matrix that is desired, and then equate term to term and see if you can solve. Okay. Now based on that, we'll solve the Puma kinematics, inverse kinematics, and then we'll move on to the next topic, which is sensors and actuators. And after that, we'll move on to basics of linear control. That will be followed by actual experiments. So these are the theoretical concepts that you require before you can move in for or to do robotics experiments. Okay, so today I'll very briefly talk about the inverse kinematics of the Puma robot, but before that I'd like to discuss about the generalized inverse kinematics problem. That is, how do we solve the general inverse kinematics problem? Okay, and then try and show how we systematically try and solve the Puma robot. So first, let me just explain the general inverse kinematics problem. That is, when we are given a manipulator like this, say for example 2 or 3 degrees of freedom, or let me take a higher degree of freedom manipulator. Basically, this is the nth frame. So this is, let me call this the n frame. So let me say that there could be more links here. Okay, so this can be n degrees of freedom system. So this is an n degree of freedom. N can be 5, 6, 7, whatever. Now what we do is we assign parameters as per DH. So first of all, as per DH, we assign the axis, and then after assigning the axis, we write the DH table. So assign DH axis, or rather as per DH parameters, or we assign axis, and then we make the DH table. Okay, so in this manipulator, what we can do is we are going to assign the axis as per DH, that you know how to do that. So Z0, Z1, and then X0, X1, etc. Okay, so I will not write the rest. So we assign the axis, then we make the DH parameter table. After making the DH parameter table, we basically find the relation between the end effector position orientation. So we find each of these matrices 0 to 1, T1 to 2, like that up to the last one, n-1 to n. Then we multiply all of them out and we get the matrix T0 to n. Okay, so this will be a matrix which will be a 4x4 matrix. Okay, so this will contain the rotation part, this will contain the translation part, this will be 1. Okay, then what we do is we are given the position and orientation, the desired position and orientation of the manipulator. Okay, so what we do after that is we equate the T0 to n matrix with that of the desired position and orientation matrix. Okay, so my desired orientation position will be, this will be numbers, or this will be numerical values, so this will be numbers. Okay, and then we try and solve term to term. So what we'll be getting is, on the left hand side you'll get this matrix T0 to n, and on the right hand side you'll get the desired position and orientation matrix, which is 0, 0, 0. This is the rotation matrix, and this is the translation matrix. Okay, so this is 4x4, this is also 4x4. So what we do is we equate term to term and try and solve, and then what we do is we equate term to term, and then we try and solve. So equate terms and try to solve. Okay, So what we'll be doing for the Puma robot is essentially we'll be following these steps. These are basically the general way an inverse kinematics problem is solved. We basically form the DH table, then we make the final matrix, and from there we basically find the matrix relating the end effector position orientation, then equate that matrix to that of the desired position orientation matrix, which would be numbers, of course. Okay, and then we try and solve one by one. Okay, so let us look at a general example of which will make it clearer before I proceed to the Puma. So I just want to make this clear before I go to the Puma robot. Okay, so suppose this is my manipulator. This is 3 degrees of freedom. Okay, and it has 3 arc joints. So first thing we do is to put our DH parameter table. So we put our DH parameter table. Okay, that's my Z0, Z1. This is X0. This is X1. This is my Z2. This is X2. Then this one is Z3, and that is my X3. Okay, this problem we have solved quite a few times before. Now, this is the position and orientation of the end effector or the last frame. In this case, let me say 3 versus 1. So after this, what we do, we make the DH table. So I make the DH table. So in the DH table, what do we make is we get A alpha, D and theta. This problem I have solved even before. So please refer to more detailed discussion. I'm doing it fast here. So this will be 0, 0, 0. This is theta 1. This is L1, 0, 0, theta 2. This is L2, 0, 0, theta 3. Okay, that's my DH table. Now, with each of this, I'm going to make my transformation matrices T0 to 3, and I'll make T0 to 1 into T1 to 2 into T2 to 3. Okay, this is something we have done before. Okay, now when I make these matrices, each one corresponding to one row of this, and multiply them out, what would I get? T0 to 3 matrix is equal to cos 1, 2, 3 minus sine 1, 2, 3. Here it is sine 1, 2, 3, and here it is cos 1, 2, 3. That is 0, 0, 1, 0, 0. And here it will be all 0, 0, 0. And this will be 1, and this is L1 cos 1 plus L2 cos 1, 2. And this is L1 sine 1 plus L2 sine 1, 2. This is 0. Okay. Now this is my matrix T0 to 3. Okay. Now what will we do? We will equate this matrix to the desired position and orientation, then try and solve. What do I mean? On this side, let me write T1, 2, 3 minus sine 1, 2, 3. And here it is sine 1, 2, 3 cos 1, 2, 3. I'm rewriting it again. This is 0, 0, 0. This is L1 cos 1 plus L2 cos 1, 2. L1 sine 1 plus L2 sine 1, 2. This is 0, that is 1. Okay, and this is equal to the desired position and orientation. This is my desired position plus orientation matrix. Okay, so this is also 4 by 4 matrix. This is 0, 0, 0, that is 1. But this will be numbers now. 1.366, for example. This is the same problem I solved. Here we can say 0.86 minus 0.5. It is 0.5, 0.86, 0, 0, 1, 0, 0. Okay, so this is my desired position and orientation of this manipulator. Now we have to equate term by term and solve. Okay, so so what do we do is we normally try and see how can we solve. Say if you try and equate this term and this term, you'll not be able to solve. So it is cos theta 1 plus theta 2 plus theta 3 is equal to 0.86. You cannot solve this equation, okay, because there are 3 variables here and there's only one equation. There's a cos. Okay, so you cannot solve. So what we do is we equate at the extreme right hand side. This is equal to that. That is equal to that. That's the way I solved it in the last class. Please have a look. So L1 cos 1 plus L2 cos 1, 2 is equal to 1.366. And then it is L1 sine 1 plus L2 sine 1, 2 is equal to 1.366. So squaring and adding these two, we can get theta 2 and then we can get theta 1. And then what I do is I use this one. So once I've got theta 1 and theta 2, I can find theta 3. Okay, so this is the way we solve for a general inverse kinematics of a robot manipulator. So this is the matrix relating the nth frame, the nth frame to the 0th frame. So in the case of the Puma, it will be 0 to 6 because there are 6 degrees of freedom. This one is my desired position orientation. This is the orientation matrix. This is the position matrix. In this case, position of what? Position of this point here. Okay, that is the position of that third frame here now. Okay. So the way we solved it in the last class is I simply put the values of x, y and said that this is my x-axis. That's x0, that's y0. And I said xy was equal to 1.366 and 1.366. And then we solved it. Okay, that means I use these two equations straight. But this is the general way of solving it. Okay, I hope you are able to correlate. How do we solve? Okay, let's move on to the PUMA now. So the PUMA is a 6 degree of freedom system, as I explained in the last class. Okay, and it has 6 revolute joints, 6 arc joints. Now, each of these joints have 1 degree of freedom, and the first one is here. That's my theta 1, that is theta 2, this is theta 3, theta 4. Then in short, we are showing theta 4, theta 5 is that side, theta 5 is that side, theta 3 is that side, z3 is that side. This was my theta 3. That's theta 3. Then this is my theta 5. This is theta 4. And theta 6 is also on this side. Z6, theta 6 is also on that side. So based on the convention of DH parameters, we can make the DH parameter table. Okay, so we see that Z0, Z1 is in the same direction. So this is the first row. Then we see the Z2, there's an angle of 90 degrees clockwise. Okay, so it's a minus 90. Okay, and then we have, so Z2 is along this, Z3 and Z2 are parallel. Okay, Z2 and Z3 are parallel, so there is no change here. Then again, Z3 and Z4, if you see, Z3 is this side and Z4 is this side. So Z3 has been rotated by 90 degrees clockwise, so it's a minus 90. Okay, and then again Z4 has become Z5, which is anti-clockwise, so it's minus 90, plus 90, and then clockwise again, so it's become minus 90. And these A, Ds are the link lengths and the offsets, and the variables are theta 1 to theta 6. So this is the DH parameter table. And based on this, what we can do next is I can put it in the generalized matrix and get the general. So what do I need next? What I need here is I need to find 0 to 6 now, this matrix. And that I can find, this is T0 to 1, T1 to 2 like that. This is T5 to 6, and then multiply them out. Okay, so now what we have to do is I need to find each one of this, for which I take the first row, put it in the generalized matrix. The generalized matrix, which I had explained a couple of classes back, I minus 1 I. So this is a generalized matrix where I can put in the values of the first row and get the matrices. And what we get is these 4 matrices here. Okay, so this is my T first, second, third, fourth, fifth, and sixth. Okay, so these are the 6 matrices corresponding to the 6 relating the joints, the 6 joints. Now, something to note here is that T06 is made up of 6 matrices: T01 into T1 to 2 into T2 to 3 into T3 to 4 into T4 to 5, 4 to 5 into T5 to 6. Okay, so these are 6 matrices that we have to multiply. Now we multiply in a particular sequence. Okay, this is something very, very important to note. Now, why do we do that? It will become clear. If you don't do it like that, you cannot solve the system of equations. Why? We'll see as we go along. So the way we multiply is we multiply from this side. We multiply these 3, then we multiply those 2, then we multiply this. Okay, so if you do that, this is 4 to 6. Okay, and then this is 4 to 3 to 6. This is the matrix 3 to 6. Okay, there is this one. Okay, so what we get is this. Okay, now if I multiply 1 to 3, 2 to 3 rather, so 1 to 3 is given here, so 1 to 3 is given here. Okay, I get this, so I multiply this, I get T1 to 6 is equal to T1 to 2 into T3 to 4. Okay, so I multiply this and then multiply this into this one now. Now what we get is this matrix. Now each of the terms R11, R12, R13 are shown here. So this is R111, that is the first term. So what does this show? If I write it in full, it is cos theta 2 plus theta 3 into cos theta 4 cos theta 5 cos theta 6 minus sine theta 4 sine theta 6 minus sine theta 2 plus theta 3 sine theta 5 sine theta 6. Okay, so there are how many variables here? Theta 2 is a variable, theta 3, theta 4, theta 5, and theta 6 are there. Okay, now if you look at this, each of the terms, they all contain sine cos except this fellow here. That is something to note. Okay, except that term, which doesn't contain any size of sine or cos, and d3 is a constant, right? It's a distance. So this is a constant. It's a distance. It's the offset distance. Okay, now this is interesting, that if you multiply it 0 to 6, now if I multiply this into, if I multiply t 0 to 6, t1 to, sorry, 0 to 1 into t1 to 6, okay, so 1 to 6 is this one, okay, the one here. If I multiply it with this one, what will happen is you get the next set of equations, the complete one. This is t0 to 6. Now here you see that all terms contain sine and cos. So something to note, that all terms contain sine and cos terms. Okay? Okay, everything here contains sine and cos terms. Now if you multiply it this way and then try and solve and equate this to the desired position orientation, you will not be able to solve. Nobody has been able to solve it. Okay, whereas if you do it the other way around and observe that this term doesn't contain a sine and cos, so what we can do is, in this equation here, if I want to remove this particular term, what will I do is I'll multiply it on the, I take it to the left hand side and multiply with the inverse. Okay, so that would basically mean the way we are trying to solve. Okay, so the way we are trying to solve, we wish to solve this set of equations. So I'm going to equate this, okay, to my desired position orientation. These are numbers. Please be careful. Please note that these are numbers. Okay, this will be some numbers. Let's say x, y, z. Okay, x dash, y dash, z dash, and x dash, y dash, z dash, and there will be some numbers here. Okay, so this is desired position and orientation. These are numbers. So these are numbers or numerical values. Let me call them numerical values. Okay, so this will contain the coordinates and this will contain the rotation matrices of the. Now if I try and equate it straight, I will not be able to solve. Equate term to term. So if I equate this to this term and try and solve, I will not be able to solve. Because you see that px, where is px? Px is here. It contains theta 1, theta 2, theta 3, theta 4. So in various orders here. So if you equate this to px, if there is a number 0.5, you can't do anything. You cannot solve it. Whereas if you look, if we try and remove theta 1 from here. So how do I remove theta 1 from here? I take theta 1 from here and I transfer it onto this side, the other side. How do I do that? I take an inverse of this. So if I take the inverse of theta 1, it comes on the other side. And on the right hand side, you're left only with theta 2 to theta 6. Okay. So on the left hand side, what we get is this term. Okay. So this is what we get on the left hand side. This is the inverse. This part is the inverse of t0 to 1 inverse, or the inverse actually. Okay. So this is what we get, and on the right hand side you're left with t1 to 6. Now if we equate the 2, 4 elements, now we can equate a term to term. Okay, this matrix is which matrix? This matrix is this one. So this matrix is this one, t1 to 6. So these are the terms. So if I equate this term now, this fellow, which doesn't have a sine and a cos, I start from there and say that this 2, 4 elements from both sides of 5.6. So if you take 2, 4 elements, so this is 2 into that, you get is minus sine px plus c1 py is equal to d3, is the 2, 4 element. So what is the 2, 4 element of that? The 2, 4 element of this is equal to this term. So that's the 2, 4 element, right? That is the 2, 4 element, that term. Okay, so what we get is this is equal to d3, which is a constant, which is a number, numerical value. So now we have only one variable theta 1. Okay, and we have one equation, so we are able to solve it. So you can solve this. Now once we solve it, then what we do is we equate 1, 4 element and 3, 4 element from two sides of that. So 1, 4 element is which one? Sorry, 1, 4 element is so we change the 1 into 4 element, 1 into 4 element. And so there is one equation, 1 to 4 element into 1 to 4 element of this one is this one. So pxy, this one. Okay, so then we equate, we get one equation. So I get one equation from here. Then I equate 3, 4 element. I get one more equation. So this is one equation, this is another equation. What are the two variables here? Theta 1 is already known. Okay, what are the two variables? Theta 2 and theta 3. Okay, theta 2 and theta 3 are left. Now we can, these are two equations, two unknowns, so we can multiply them. We can square and add and solve. Look at the way we had solved for the 2 degree of freedom manipulator. So from here I can get theta 3, then I can get theta 2, and that order I can go and find. So I've got theta 1, theta 2, theta 3, then I can find theta 4, theta 5, and theta 6. Okay, that is the inverse kinematics solution. Now how many solutions will be there? So depending on where you are in the workspace, so you can have as many as 6 solutions sometimes, okay, because there are 6 variables, and in the center of the workspace you can have as much as 6 solutions, okay. Now if you look at this, and yeah, so this is one. Now I am not going to go any more into details of this. We are not required to do inverse kinematics in this course, but when we do the robot programming in the end, the industrial robot, when we go to the experiment, then basically the robot controller already knows the inverse kinematic solution, okay, and we just have to figure out which solution it is going to take. So if there are 6 solutions, it will take an energy optimal solution. So which one is the nearest to the previous solution, that is the solution it will take, okay. Now if you are interested in knowing the exact procedure of solving the other solutions and how do you get all the solutions, please refer to the textbook Introduction to Robotics. So Introduction to Robotics by John Craig, sorry. Okay, please refer to this. This has all the details of the inverse kinematics of the Puma. For us, it is enough to know this much only. Okay, let's move on now. Now I move on to sensors and actuators. Now we see that our objective is to do experiments, and we need to know how does a robot move. So how a robot moves is, if we have a robot link like this, a robot manipulator, at every joint, okay, so if I consider this to be a joint, then there is a motor, there is an actuator, which is an actuator, then there is an encoder or position sensor and a gear in front. You give voltage to the motor rotates, and it goes from one position to the desired position. Okay, so basically the controller must know how much to rotate the angle to take it to the desired position. Okay, now at every joint there is one sensor and actuator pair like this. So on the other joint there will be one more. So this is also called independent joint control, which means that the joints are independently controlled, and each of the control structures in the joint is looked like this. It looks like this. So there is a controller, there is a motor, which is an actuator here. Okay, there is a motor. Then there is an optical encoder, which is a position sensor. Okay, and this is my feedback closed loop feedback system. Okay, so whatever is the desired position, I'm going to give input here. This is my desired, theta desired. The controller will see what is the present position, which is theta present. Then it will do theta desired minus theta present, find the difference or the error, and then give it to the motor. The motor will rotate, this will move. And then, so if I can imagine that if this is my position 1, and I want it to go to the position here, which is 10, then it is at position 1. So it will become 1 minus, sorry, the desired is 10. I want it to go to 10. Present position is 1. So 10 minus 1 is 9. So the motor will rotate by 9 and it will give a voltage to the motor. The controller will give a voltage to the motor, and the link will rotate and it will go to the point until it goes and reaches the point 10. So as it is moving, the position sensor is giving feedback. So it will give 10, it will give 1, then 2, 3, 4, 5, 6 like that. So it will become 10 minus 2, 10 minus 3, 10 minus 4 like that. Okay. Now that is how each of the joint controllers work. Now if you look at the basic control system diagram, then our basic control system diagram will look something like this: plus, minus. This is the controller. Okay, and this is my the robot joint plus a motor. Motor would be there. Motor plus joint of the robot joint. It comes back, and here there is a sensor. Okay, and the sensor is giving feedback here. So whatever is my desired position, desired theta desired and theta present, okay, it is going to go like this. It will come like this, and this is a comparator which is doing theta d minus theta p. Okay, so what we see is that how a controller works is, sorry, not the controller, this is a comparator. So the comparator basically compares the desired to the present position and then gives it to the controller. The controller amplifies it and gives it to the motor. The motor rotates. So as I was saying, that if my joint is here and this is my motor, okay, suppose it is only one link. I want it to go from here when theta present is equal to 10 degrees, and I want it to go here where theta d is equal to 70 degrees. Okay, then basically it will do theta d minus theta p equal to 60, and then it will actuate the motor. The motor will rotate until it comes here. Now as it is moving, the sensor feedback is coming, so the theta d minus theta p is going towards 0. Okay, the moment it reaches 0 means it has reached. Okay, so it will immediately stop. So that's how it knows where it has reached. Okay, now the other point that we have is so this is what the actuator sensor pair actually looks like an actual robot. So there is a motor which is AC or DC motor, which is given here. So this is my motor. Okay, now the motor is given voltage. Okay, and in front of the motor there's a gearbox. The gearbox is used to increase the torque and to reduce the speed. And the back side there's a position sensor. In this case it's an encoder. Okay, so we have an actuator, a motor which is an actuator here. We have a gearbox and we have a position sensor. All these three things combined make up an independent joint control system. Okay. Now, before we proceed further, a couple of things. First of all, I just showed this. So this is also called independent joint control. Independent joint control. Okay. That means each joint is independently controlled. So if you have what this also means, okay, I'll just come to that. Independent joint control. And the other is that this is a single input. Okay, so which is also called a SISO system, or a single input, single output system. Now this is essentially an assumption that we are making. Okay, robot control is actually not single input, single output. What do I mean by that? And also the other part, that why is robot control difficult? So if you look at the robot structure, suppose there are many links in there. Okay, now there are position, velocity and accelerations. Now because each link is connected to the other link, what will happen is when the links rotate, the velocities will affect the next link. So if this is having a velocity of theta 1, this is having a velocity of theta 2 dot, then the effective velocity of this will become theta 1 dot plus theta 2 dot. Why? Because the velocities are propagating in that direction. That means every link, the previous link, is affecting the next link now. Okay. Now what you might be wondering, so what? So it basically means the acceleration and velocities are moving. Now if they are moving, then what is happening is that, so if they're moving, what is happening? Because of the accelerations moving, the inertia forces will come because the links have mass. So there will be inertia forces which will be acting at the CG of the links now. So this motion is going to cause inertia forces to come into the picture now. Okay, there will be other kind of forces because it is rotating. So there will be Coriolis forces, centrifugal forces, and there is gravity force, of course. Now, if there is any force which is acting, what will happen? This force will cause a moment on that joint, and this moment will start moving in that direction now. So velocities move in this direction, forces move in that direction. Now, the controller, which is here, is basically a position controller. So this controller is a position controller. Okay, which means that it is only controlling the position, and it is independent joint control. So it doesn't know what the other links are doing. Okay, there is no way. So effectively, whatever is happening in terms of the torque is acting as a disturbance on the controller now. Okay, now I might give an example here. Suppose this is an experience you would be having. I'm sure you have this experience. So when you're moving your arm like this, you're moving your arm, okay? So when you're rotating your shoulder, suppose I'm rotating my shoulder with some angular velocity theta 1 dot, okay, and this joint is not moving. But because this joint is moving, this joint will also be subjected to a force. Centrifugal force will come on that joint, okay, although the joint is not moving. Not moving means this angle is not changing. Although this angle is not changing, it is still subjected to a force. And this poor controller has no way of knowing because it doesn't know what the shoulder is doing, okay, and this acts as a disturbance on the system. So if I write my dynamic equation, the total equation is equal to the inertia forces plus Coriolis into centrifugal force plus gravity force. Okay, this is my gravity force. So this is inertia forces. This is Coriolis plus centrifugal force, and this is my gravity force. Okay, so all of these forces, and if there are external forces, it will become J transpose F. So what would happen is all of this would act as a disturbance on your system now. Okay, this is acting as a disturbance on the system now. Okay, what is the disturbance doing? It is trying to disturb what the position controller is trying to do. Okay, so whatever the position controller is trying to do, this dynamics of the system, that is essentially because of the dynamics, it will tend to disturb. So if you look at the actual closed loop control system, you have one input which is here, but there is one more input which is there. And this input is plus plus, which is tau, which is coming from that side, and this is my disturbance. So it's a multi-input system. There is one input here and there's another input there. Okay, so the port position controller has to deal with this fellow. Now we make the assumption that this is equal to 0, and we'll consider this to be a... Okay, so what we are seeing is that we make the assumption that the disturbance is equal to 0 and proceed. But in reality, the disturbance is not 0. Okay, and that is what something which makes robot control very, very difficult. So if you are simply using a single input, single output system with a position controller, okay, then it is difficult to control actually. Okay, just keep this in mind. That's all as we proceed to the experiments, as we'll be proceeding to the experiment after some time. Okay, now let's look at the basic elements that I drew in my control system. So you have in the basic control system that I drew, so you have a comparator which is a plus minus here. Then we have a controller. Okay, we have a controller. Then we have the robot joint itself with the motor. So robot joint with the motor. So this is my robot joint with the motor. And then there is a feedback sensor, which is my sensor here. Okay, so this is my sensor. Okay, so that is my sensor. So this is my theta desired and this is my theta present. Now this has how many elements? Number one, it has sensors. That is my sensors here, which you can look at the sensors. They are indicated here. Why is the sensor required? Because it has to tell the controller what is the present position of the robot joint. Actuators, there is a motor connected here, so there is a motor there. So that is my actuator. Controllers, this is my controller, which is actually deciding how much voltage should go to the motor. And then there is a system model, which is the robot joint itself. Okay, so these are the basic elements. Now, if you look at this control system diagram, this is a closed loop control system diagram, you basically observe that the input from here is electrical. Okay, that means in terms of voltage, which is going to the motor. Now, what is the output of the motor? The output of the motor is motion. Okay, that is physical motion. So the output is the electrical energy going to the motor. Okay, is this my motor? The output is motion, which is physical motion. Okay, so output here is motion. Okay, that means the link is moving. Now this controller is electrical, so it understands only electrical signals. So it does not understand physical motion. So this motion has to be converted. So here there is motion. So this motion is converted to electrical energy again. Okay, so electrical energy, so the motion or the mechanical energy, let's call it mechanical energy, is converted to electrical energy again. So here it is mechanical energy. Okay, so what is actuator doing, or actuator doing? It is converting electrical energy to mechanical energy. What is a sensor doing? It is converting mechanical energy to electrical energy. So what is the general definition of a sensor and actuator? The general definition of sensor and actuator is it converts energy from one form to another. In this particular case, we are converting electrical energy. So electrical energy to mechanical energy. Okay, electrical energy to mechanical energy. That is an actuator. Okay, and what about a sensor? Sensor is doing the reverse, is converting mechanical to electrical is a sensor. Okay, so this is a very general definition of actuator and sensors. It basically converts one energy to from one form to another. Now there is also a term which is called a smart actuator. So smart actuators can convert energy from an actuator which can do both. It can behave like a sensor and it can behave like an actuator. Okay. Now in terms of control systems, we have two kinds of control systems. One is called the open loop control system, in which there is no feedback, which is shown here. So there is no feedback. Okay. For example, if I give a very small voltage to the motor, it will rotate a little bit. Now, if I know how much voltage if I give, it will rotate how much, then approximately I can make it rotate. Okay. Say, for example, if I have a pulse width like this, okay, and if I know that if I give this much pulse width, okay, then it will rotate by 1 degree. Then I give 1 degree here, 1 degree here, 1 degree here. So if I give a pulse like this, it will rotate 1 degree in steps. Okay. Now this is an approximate way, but it can still be done that way. So this is an open loop device, an open loop system, which is called open loop. So this is what we call by an open loop system. This is not very accurate, but it is cheaper. Now this is a closed loop system. This is closed loop because you can see that the feedback is coming back. So this is my closed loop control system. Okay, and we'll be looking at this one mainly, the closed loop control system. Okay, so first we'll talk about sensors, then we'll talk about actuators. So the basic classification of sensors are as internal sensors and external sensors. Internal sensors are required for the basic working of the system, and external sensors are required for interaction with the environment. Now, if you look at this, what I had just explained is that if you have a robot, how does the robot actually work? Is that at every joint there is an independent joint control which has a motor, it has an encoder, and it has a gear in front. Okay, and how does the robot move from here to here? Okay, so basically, if I'm here and I want to go there, it will do inverse kinematics there and find out what is the corresponding thetas. Okay, suppose it is theta 1 is equal to 20 degrees and theta 2 is equal to 60 degrees there. Then what it will do is it understands that it has to go to theta 1 equal to 60. Then what it will do is the controller understands that it has to give the voltage to the motor such that the link moves like this by an amount of 40 degrees. Okay, so it will do 60 minus 20 equal to 40, move the link. Now, to understand the position at a point, it needs position sensors. It needs to know the position. So it needs a position sensor. Now, when it is rotating, the motor has a velocity. It also needs to know the velocity. So there is a velocity requirement, or there is a velocity sensor. And sometimes when it's moving very fast, you also need acceleration sensors. So you may also need acceleration sensors. Now, without these sensors, the robot cannot work. Because if it doesn't know the position of the link, there is no way it will know where the end effector is. So without a position sensor, the robot cannot work. So these sensors are called internal sensors. They are required for the basic working of the system. Okay. Now, suppose this robot is performing a task like it is pressing against a wall. Just for example, there is a wall there. It's pressing with some force F. Now it will need to have some kind of a force torque sensor at the wrist also. Okay, so this force torque sensor will tell the robot how much it needs to press against the wall. Okay, and this is required for the task of applying a force on the wall. Now this is an external sensor. So if this sensor is not there or is not working, the robot will still work, but that force control ability will come down. Okay, so external sensors are required for interaction with the environment. For example, force torque sensors, computer vision. There can be a camera mounted. Okay, then touch sensors. So these are external sensors. So first we'll look at internal sensors, because these are the ones that are most commonly used in robots, and these are the ones that robots without which the robot cannot work. So the sensors used for closed loop control are called internal sensors, and they have to measure position, velocity, acceleration. These are the various sensors that are there: potentiometers, encoders, LVDT, tachometers, accelerometers. In our experiments, we'll be doing experiments with each one of this. Physically, you have to connect the potentiometer, rotate and see how it is changing, how you're reading it using a microcontroller. So the first one is a position sensor, which is a potentiometer. Now, potentiometers you would have studied in school, I'm sure. How it works is very simple. So there is a resistance coil and there is a wiper which moves on the resistance coil. So this is a resistance coil which is here, and there is a wiper. Now, if there is a robot link like this, okay, what I can do is I can attach the link to the wiper here. So when the link is moving, the wiper is also moving. Now, when the wiper moves, the resistance from the small r, which the resistance is from here to here, that changes. So there is a total resistance which is from here, that is the total resistance which is going here. The capital resistance R from here to here. So there is a capital resistance or a total resistance R, and there is a small resistance R. So when it moves, the wiper comes like this, and this R will change. That one will change. So if I give, then you get a V out which is proportional to the small r divided by capital R into V in. Okay, so this is my V out, which is the resistance coming from the small r. So what we can do is we can calibrate this system for different positions. Say, for example, when the wiper is here, we can say it is 0 degrees. When the wiper is there, I can say it is 180 degrees. So I can calibrate it by saying from 0 to 180 degrees, what is the voltage? This is my voltage, and I get a straight line. So now for an unknown position, suppose I know the voltage is this, then I can see what is the corresponding angle from that calibration. Okay, so that is how we use a potentiometer. Now potentiometers are very cheap. Okay, and they are very simple to use. Okay, however, they have problems. One problem is that they wear out easily. Why do they wear out easily? Because there is continuous contact here. So when it is moving, what will happen is the contact will wear off. And number two is it will wear out easily, and then we have the other thing that we say is there is noise at the contact. Why? Because there is physical contact being made. So when you're reading it using a microcontroller, there is chance of noise coming in. Okay, that means stray signals or. Okay, so potentiometers are very cheap, very simple to use, but they are not used in industrial robots. So they are not used in industrial applications. Okay. Now you can also have a linear potentiometer, which is shown here. So this is a linear system. This is a wiper, but this wiper moves in straight lines. It can move like that. Okay. So this is and the principle of working is exactly the same. Now the most commonly used is an encoder. Now what is an encoder? As shown in this wheel, in this figure here. So there's a wheel which is rotating. So there is a wheel, and this wheel has holes. Okay. Now if I draw the side view, on one side you can see that there is an emitter. So this is an emitter here, and on the other side there is a receiver. So this emitter can emit infrared or light. The receiver receives light. It's something like a photocell. So this is a wheel which contains holes. So whenever the light goes through, it gives a signal of 1. Whenever light is not going through, there is no light. The signal is 0. Okay, so which basically means voltage or no voltage, or 1 and 0. So as it is rotating, what we'll get is you'll be giving signals of 1 0 1 0 1 0 like that. Okay. Now in this encoder, suppose there are 200 holes. Okay, and for one rotation is 360 degrees. Then by 360 degrees by 200, it is 1.8 degrees. Okay, so the distance between any two of this is 1.8 degrees. So if you know how many of them are there, and you know the distance between them, between these bits, then you know how much distance is traveled. So how much theta is there, you know. Okay. Now if you know the time also, if you know this much signals have gone in time del t, then del theta by del t is the velocity, theta dot. Now if you take the second derivative of this, so theta dot or theta dash dot minus theta dot divided by another del t, this will give you theta double dot, acceleration. So this very simple device can measure position, it can measure velocity, and it can measure acceleration. Okay, and in about 95% robotics applications, not only robotics applications, any position measuring applications like CNC machines, you can talk of, we have CNC machines, then you have robots, you have aircrafts, you have whatever, wherever you're doing position control, 95% of them use incremental encoders. So whenever you look at an industrial motor at the back, you're going to find a encoder. Okay. So it can also be used as a counter, as you can see here. It is counting how many of those bits have gone through. So the principle of working is very simple. It doesn't cost anything. And the advantage is that the signal is digital. Okay. So when we come to our experiments, we'll see that the microcontroller is a digital device. It understands digital, not analog. So there is no need for a converter here. Otherwise, you'll need, for example, if you're using a potentiometer, you'll need an analog to digital converter, because otherwise the microcontroller will not be able to read it. We have seen that the resolution of the encoder is not very high. It's about 1.8. Okay, so what we can do is we can use two encoders. Let's look at it this way. There is one encoder here, and there is another encoder there. So these are encoders. Okay. Now there are two encoders which are placed in parallel like this. Let me say there's one encoder here, one encoder here. And what we are seeing is that when it is rotating, there is a slight shift in between them. So the holes are not aligned. So when this one is giving a signal A, when encoder A is giving a signal, which is shown here, this is my high and then low. These are square waveforms. There is a slight shift in here. As you can see, there is a small shift there. So signal B will come a little bit after some time. Why? Because there is a shift in there, in between the two encoders, right? So if you look at A and B, and if you use an XOR gate, so an XOR gate basically means that if there is an input A and an input B, if there is any change in A or B, then you'll get C. Okay, if there is any change, then there'll be a change in C. So when you're looking at A and B, when there is a change in A, there is a change in C. Then A is constant, there is a change in B, so now there is a change in C. Okay, then again here A is coming down, so immediately there will be a change in C. So if you look at this time instant, there was only one pulse here, but here you're getting two pulses, which means the resolution has gone up now. So it is 360 by 200 into 2 now. Okay, so if you can use 3 encoders, your resolution will go up even more. So by using an XOR gate, the resolution of position measurements go up drastically. Okay, so in an industrial setup, normally you'll be having encoders which will have very large counts. It can have like 1000 counts per ton CPT, and it will have parallel encoders. So you can get very high resolution of the system. Okay, that is one. The second is, how is the direction of rotation measured? So we can measure the direction of rotation. What I mean is, suppose the encoder is here. Let's look at this example. If it was rotating this side or it was rotating that side, clockwise, anti-clockwise, how do you know? Because your signal will still be the same. It will be 0, 1, 0, 1, irrespective of which side it is going. So how do you know whether it's clockwise or it's anti-clockwise? So for doing that, for measuring the direction of rotation, two emitter receivers are used. So if this is my encoder, okay, which is rotating, this is one here, then one here, one here, one here. Okay, so what we see is that we are having one emitter receiver here, okay, and another one here with some phase shift. Okay, so in the side view, so there is an emitter receiver, two of them are there with phase shift. Now the moment this one is there, it gives a signal 1, whereas this one is 0. Okay, so if it is going this side, what is going to happen? This is 1 and then it will be followed by 0. If it is going that side, it will be a 0 and then it will be a 1. Okay, so you can figure out which one is leading and which one is lagging. So by a lead or lag, we can find out whether it is clockwise or it is counterclockwise rotation. Okay, now so if this one has it, suppose you're going that side, this fellow will become 1. It is 0 now, it will become 1. Whereas if it was going on the other side, just the reverse will happen. Okay, and that is how we can measure clockwise or anti-clockwise rotations. Now, something to note about here is that this is an optical encoder, incremental encoder, which basically means that it is incremental in device. So the signal is incremental. Okay, what that means is that it is 1010 like this incrementally. Okay, now with this there is no absolute position. For example, when it is rotating, encoder is rotating, for example, and the power goes off, so you won't know where the angle was because it is an incremental device. So if you need absolute position, then we use this encoder, which is an absolute encoder. How it works essentially is that in the previous case, in the previous encoder, we had only one row of holes. Okay, like this. Now in the second one, we have 4 rows. There is 1, 2, 3, 4 rows of holes. Okay. So we have 4 rows of holes, and these 4 rows of holes are the ones that give us 4-bit readings now. So we have, if I draw the side view of this, so there'll be emitter, receiver, emitter, receiver, emitter, receiver, 4 of them are there now. So in any shot, you'll be getting 4 bits. Okay, so there are 4 bits now. So there are 4 bits which are coming, which can be high or low. Say for example, in this case, if they're all 1, 1, 1, 1, 1, so they will all be 1, 1, 1, 1, 1. In this case, it is the 0, 1, 1, 1. Then that is that's a 1, that's a 0, that's 1, 1. Now each sector is unique, which means it corresponds to any one angle. So wherever it is on just one angle. Okay, so this is a unique angle, so it will come to any one angle and it will stop there. Okay, so basically what we are saying in this absolute encoder is that now suppose the power fails and you are here and you get a signal of 0 0 1 0. You know that exactly it is here because this sector is unique now. In no other sector you will get this angle, so you know it is here now. Okay, which was not possible in the case of an absolute encoder. However, this encoder is not normally used because you have 4 bits now, so that will mean that you have to keep track of these 4 bits, and the electronics becomes more expensive. It becomes more expensive, the controller. Okay, and it's not required. So what is done? We use an incremental encoder with a limit switch to measure position. Okay. Now you would have studied about DC motors. DC motors you would have studied at school itself. And how a DC motor works, you know that we give a voltage in. So I'm giving a V in, plus minus here, and there will be a voltage generated in this coil. This voltage will be there in the coil, and because of this voltage, there will be a magnetic field which will be produced. Okay, so on a conductor, when we have a voltage, there is a magnetic field produced. Now, when the magnetic field is produced on the stator, there is also a magnetic field which is moving. So the field produced by the rotor will interact with the field produced by the stator, which will cause a moment on this rotation. And that is basically how the motor rotates. Now, if I do the reverse, that is, I rotate the rotor in a magnetic field. Now, if a coil is moving in a magnetic field, a conductor is moving in a magnetic field, then an EMF will be induced in that. So a voltage will be generated. So a motor and a generator are opposite of one another. Okay, motor and generators are opposite of one another. So if you are trying to measure the speed, we can draw the graph of voltage versus speed. Okay, that's also a straight line. So whatever is the voltage, I know what is the corresponding speed. So that is basically called a tachometer. So we can have tachometers, we can have DC motors, they are opposite of one another. Okay, now the other sensors that would be required are contact sensors, for example, on-off sensors. Okay, they are like limit switches. Okay, so contact, then zero frame reference sensors, find position orientation of object. Okay, for example, the robot is here. Okay, and the robot, the power is off. Okay, and there is a motor, and there is a motor, encoder, and a gear. Now, the moment you switch it on, okay, it doesn't know where is the 000. Where is the 000 of the robot? Okay, because all the kinematics is done with reference to the base frame or the world frame, and that is taken as 000. So base frame or world frame. Okay, so how do you know where that is? So the robot wouldn't know that. So what it does is, when you switch it on, it does a motion which is called homing or calibration. So what it will do is, it will move to one side, and if there is a limit switch there. Okay, so limit switch is something like a normal switch. So it will go, and if the link hits that switch or touches the switch, it immediately knows that that's a 0 of the system. That is one. The second is, when the link is moving. Okay, this is a robot, this is a link. It goes from here and comes till here. Okay, it cannot go fully 360 degrees. It will go for about 340 degrees. Okay, and then there are stops in there, which are, there are physical, there are limit switches again. So the robot will hit that, and now it knows that is 0, that's the end of range. It goes on the other side, it knows that is 340, now that is the other end of range. So its range is this much. So for doing that, it needs to have contact sensors. Okay, contact sensors and zero frame reference sensors. So zero frame reference sensors are also contact sensors. It basically figures out where is the 0 of the system. Okay. Now, in order to find out, suppose the robot has to pick up an object from here. What it needs to do is, it needs to find out what is the position orientation of this object with respect to the base frame. Now, for doing that, it may need to have an overhead camera which can see this object and it can know its base also. So it can do image processing to find out. Okay, that is also an external sensor. Now, the touch sensors that are normally used are on-off switches. They are very similar to the keyboard, the keys in a PC or a laptop. Okay, the working principle is exactly same. These are contact sensors. If you press the key, then immediately contact is made. Okay. The other kind is emitter-receiver pairs, thermal pressure sensors, which are also there. Okay. So today we'll stop here, and in the next class we'll move on to other kind of sensors that would be required Okay, so today's class, what we looked at, we started off with the general inverse kinematic solution. That is, if you're doing a general inverse kinematic solution, how do you correlate the end effector position and orientation with respect to the robot position and orientation? The next, what we looked at is the inverse kinematics general solution for the Puma robot. Very quickly I did that because we don't require the inverse kinematics in detail here. If you're interested in knowing all the solutions, how many solutions are there, where in the workspace, you can refer to the textbook, Introduction to Robotics by Craig. After that, I looked at, we talked about closed loop, open loop control systems, sensors, actuators. We looked at some of the internal sensors like encoders. So some of this we are going to use in the experiments, because when you're controlling a robot, the controller needs the information of the present position of the link. For that, it needs an encoder reading. Okay. Now, after that, we looked at the contact sensors. Contact sensors are also required for getting contact when it has reached the end of the workspace, or to figure out where is 000. Now, there are other kind of sensors which are required for a robot. For example, a mobile robot for obstacle avoidance. It needs to know where is an obstacle. Okay, so those are sensors which are basically tell the robot where is an obstacle in front, if there is an obstacle in front, and how to navigate an obstacle, things like that. Okay, so we'll stop here today, and in the next class we'll look at sensors which are for external sensors, which are for telling the robot if there is an obstacle. Then we'll move on to actuators, and then slowly we'll move on to control systems. So we'll stop here today. Thank you.